Hello. I wanted to do some review over how we can draw graphs based on information like what we have here. So what I've actually done is just copied down the problem from page 52. I'm sorry, 51 in our workbook. This was problem B on 51 uh, in our workbook. So this is naturally something that people often struggle with, and it's been brought to my attention as well that we still don't feel totally comfortable with questions like this. So I wanted to run through an example working with this here with y'all right now. So first of all, we need to read through the requirement that it has before we even know how to approach drawing. So part one says f of -5 equals 4. Then f of x has the y-intercept at 0 and 1. So these two are special because they give us really specific particular points. They give us exactly that when we plug in -5, I get 4. So I know on my graph, I look at -5, I go up to 4, and I need to graph exactly that point up there. So I need to include this point. My graph has to go through that point. Then it says f of x has a y-intercept at 0, 1. Well, to have a y-intercept genuinely just means that's when you cross the y-axis. So it's saying we cross the y-axis at the coordinate 0, 1. Well, that is exactly just saying our function goes through that point. So we have 2 points that we know our function has to go through. It has to be that value at those 2 points. The rest of the information is almost an exercise in a little bit of creativity. So next, it says we have concave down on the interval from -5 to 0. And then we're constant from 0 to 4. And then we're concave up after 4. So one way to kind of think about this is to break this graph up across these different intervals that it's telling us to do the different things at. So we're concave down on this interval. So I know at least from here, from -5 to 0, I need to be concave down. I need to be constant from 0 to 4. So from 0 to 4, I need to just be a constant straight line. And then concave up everywhere after 4, which is already kind of marked here. That we're constant from 0 to 4, and then after 4, we're going to be concave up. So when we talk about concavity, there's really only two pictures that I think we need. This is our basic example for concave up, and this is our basic example for concave down. Now, they are, each one of them can really be broken up into two pieces. So looking just at concave up, we are decreasing on the left, right? The function's going downwards. And then to the right, we are increasing. So for concave up, decreasing looks like this, and increasing looks like that. Well, then looking at concave down, we can also split that into its two parts. To the left, our function is going greater and greater values as we go to the right. So to the left, it is increasing. And to the right, it is going downwards, so that is decreasing. So when we look at it like that, we really see that there's four kind of ingredients when we start talking about concavity. We're either decreasing but concave up, increasing and concave up, increasing and concave down, or decreasing and concave down. So it may help to kind of look at this as these four different pieces. So maybe I can even make a table if this helps. Increasing, decreasing, concave up, concave down. So increasing and concave up looks like this. Decreasing and concave up looks like this. Increasing and concave down looks like this, while decreasing and concave down looks like that. So it's almost like we have these four pieces that we need to assemble to make our graphs. So in this case, it doesn't actually tell us that we have to be increasing or decreasing. It only tells us about the concavity of our function. And that kind of gives us a lot of freedom. We can be increasing or decreasing in some sense. However, it very subtly does kind of demand some sense of increasing or decreasing, with the fact that we have to connect our dots from here to here. So if I'm trying to connect from the point -5, 4 to 0, 0, I'm sorry, 0, 1, obviously this is going downwards. So we need to be decreasing. But we also need to be concave down on this interval by that instruction right here. So if we need to be concave down while connecting these two dots, then there's only one way to do that, and that's with an arc like that. Maybe I make it a bit more sharper. See, that is how we can be concave down, but connect our two dots. Next, it says that we need to be constant from 0 to 4. Well, one way to do that is to not change the value that we're already sitting at. To be constant means they're just going to be a straight line. So it would still be accurate if I drew this straight line along 0 to 4. I'm constant, but this is what we call like a piecewise graph. And for our intents and purposes, it is perfectly valid. Nothing here said that we had to be continuous. So what I just did is perfectly fine. We can draw that constant line wherever we want from 0 to 4. But I am going to draw it in a way that keeps the graph continuous. So I'm just going to draw our line right along from those points that we already knew. So from 0 to 4, for our x values, we're just constant. We are a single value. Next, we have to be concave up for everything after 4. Well, looking at this chart that we have, to be concave up, we really have two options. We can start increasing or we can decrease. We can look like this however we want. And again, I say however we want because nothing really tells us that we need to be increasing or decreasing. There's no 2 points that we're trying to connect the dots from. I can do it however I want. I just have to be concave up. So one easy way to do that would just be, well, I guess I can just go upwards and go forever and on from there. It also would have been perfectly valid, I'll do this in red, to be decreasing, to be concave up, but decreasing, to start doing something like that. That would also be perfectly valid. Sure, it doesn't look as nice, but that doesn't really matter. Either way would have been fine. So this is kind of the most expected answer for this kind of question. But obviously how sharp you really draw the concavity doesn't matter. For instance, you could decide to go like that really quick and say concave up. That's a bad arrow, but you could do concave up like that. You could do concave up like that. Really anything. And again, you could even start decreasing but concave up. I'm sorry, that's concave down. Decreasing but concave up in any way like that, however sharp you really wanted it to be. So however we draw it, but I think that earlier approach like this might be the most natural way to do it with whatever kind of sharpness that you want to it there. Okay, so this is me just going through exercise B. to help us wrap our minds a little bit around these kinds of questions. So, yeah. And again, if we had specific requirements about what we had to do elsewhere, then we could fit those in. So say, for instance, it told us that let's add this in. Let's say it told us the range is, let's say, -1 to infinity. Now, the way that I've drawn this kind of already fits that condition, that this arrow is going up, that our function is going to go up and up and up and up forever and ever and ever. And it's going to be perfectly fine. So now the lowest that I'm going to be is, I'm sorry, I meant to do +1. The lowest that I'm going to be is 1, and I am increasing without bound. I'm going up and up and up to infinity forever and ever. Now, another way, let me try and get rid of there. Another way that we could have done this is, what if it said the range actually only went up to 4 and we go down to -infinity. Now what I have for my graph is no longer valid, because I can't just go up and up and up forever. And also, I need to go to -infinity in some way. Well, one way that I can do that is the other way of doing that concavity. So if I need to be decreasing, I need to start going downwards, then I could make my concavity kind of like this, but say we're decreasing forever and ever and ever. There's not an easy or good way of drawing that, because we often try and act like this kind of tapers off to one point when we're decreasing, but we don't really have to. And this is obviously a bad example because I just thought of it. Well, let me try and, there we go. Okay. Another way that we could achieve this range is by actually saying that, well, let's be concave up for everything after 4, and it's not acting like this should ever stop. So let's just be concave up, but let's go ahead and maybe taper off to this value like that. We're still concave up because we're like doing like that. It's just kind of leveling out almost, but not really. Another way to get to -infinity is to go ahead and draw downwards like that. So there really is a lot of creativity as to how we achieve the requirements that these questions give. If I add in this condition, there's multiple ways that we can try and achieve that. And I think that makes it interesting. And also intimidating, because there's multiple ways that we can approach the same answer. Everyone's going to draw a different graph. So that makes it fun and intimidating in some sense. But really, this isn't too bad. We just know that there's a few pieces that our graphs can look like, and we just try to attach those together. So these are kind of this table is a good table for like concavity, but functions don't always have to have concavity. Sometimes a function can just totally be flat. So kind of like where we were constant right here. There's no concavity to just a straight line. So we can be concave up, concave down, or we can be neither. And we can be neither in a few different ways. So here I can say no concavity. Increasing. Decreasing. Or constant. So if we have no concavity, so just a straight line that's increasing, this is our most basic example of just a line that's going up. If we have no concavity and we're decreasing, then we're just a straight line going downwards, And if we have no concavity and we're constant, well, then we're just a flat line, just a constant function like that. And again, I think these are the most obvious examples that we have in our heads, the most readily available examples of just increasing, decreasing, right? These are just our normal traditional high school lines that we can draw. So to that end, I think these are good examples. But something that might be worth pointing out is to be constant. There's only one way to be constant. You cannot have any concavity if you're constant. Concavity only exists in increasing or decreasing. So whenever you say you're constant, you know you have to look exactly like this. There's no real creativity with constant beyond just like what value you really place it at. Sure, I could be constant up here, constant down here, but I just chose to be constant right here, just to make it a continuous graph, which it doesn't need to be. Does not need to be. Okay, so this is my review and over explanation for this kind of situation. Hopefully I didn't make it worse, but hopefully I cleared some stuff up there. All right, very good.